Okay, so introducing myself, my name's Derek Miller. I'm with ARM, based out of Austin, Texas, and I'm part of our systems research group, which is part of our architecture and technology group. To give you, if you understand ARM's corporate structure at all, that'll mean something to you. If you don't worry about it. I work on research and in research, and I've been doing it working on confidential computing for the last 4 or 5 years at this point. And so mostly I'm going to go through here. I'm going to start with how to trust. Actually, the whole concept is how to trust somebody else's computer. And so to put it into some historical context, I'm going to talk a little bit about the history of data protection. If you're old enough, you remember logging into systems using Telnet and using FTP. And I can tell you that I remember logging into Lawrence Livermore National Laboratory across the open internet using Telnet and our login. So, and that was an HTTP. This is what it used to be like, and everybody accepted it because that's all we had. But then slowly, we changed that. We changed it from Telnet and our login to SSH, from FTP to SFTP, and from HTTP to HTTPS. This is about protecting data in transit. So whenever anything goes across an open network or even a closed network, oftentimes we'll protect things with TLS, IPsec, or MACsec. So things have changed. There's been a lot of hitches along the way. Everybody knows, if you're paying any attention to the TLS, there's been a lot of changes in the protocol and changes in how things are done and changes in Cipher suites as we've learned more and more about that topic. Now, the next topic is protecting data at rest. Used to be, it was very weird to have an encrypted disk, but these days it's basically just de rigueur for any corporate environment. So we've changed the way we think about data at rest, but we still have at least one more frontier to go, and that is, what about protecting data in use? So that's what confidential compute is all about. What we could do is we could keep everything on premise. So we own the computers that we were running our workloads on. But who really wants to go back to that? Well, I think maybe HP, but there's a lot of companies that might. But in general, the cloud environment and edge environments are here to stay. So how can we make sure that we trust them? One solution, which I love technically, do not get me wrong on this, is fully homomorphic encryption. And this is an encryption technology that allows you to perform operations on encrypted data without exposing the data to the entity performing the computation. This is really interesting from a cryptographic perspective, but there are a few downsides to it. One of them is the data size increases by orders of magnitude. We're talking 1,000 or more in size. So when you transmit that data across the network in encrypted form, it blows up. And then in memory, it blows up. And also, your performance decreases also by orders of magnitude. You have to perform the operations on all the bits of that encrypted data, which is larger. And then additionally, because you don't want to expose the nature of the data, you can't actually perform branches on it. So you have to circuitize the computation, which means that every possible branch you may want to take has to be computed as well. So this increased size, this increased computation complexity means that your power consumption will also increase by the orders of magnitude. There's a lot of work going on in this area. I find it extremely fascinating, but I'm very dubious that it will ever be able to get down to the efficiency that you can get with a normal CPU. Just because of the nature of what you're doing. That being said, keep your eyes out in this area because there's a lot of very fascinating work going on that. There's some projects on hardware acceleration of fully homomorphic encryption. But I believe that the more practical approach to what we're doing is confidential computing because of the better scales and the better power consumption and performance that you're going to get from it. And also, you can do confidential computing now. So how do we establish the trust in someone else's computer when we're not operating on encrypted data on the system? So the Confidential Compute Consortium, which is part of the Linux Foundation, has their own definition here. We don't have to read the eye chart here. That being said, they've got their own definition, which includes the concept of attestation, which I'll go over that. ARM's internal definition, which they made me put in here because I work for ARM, is confidential computing is the protection of data in use by performing computation in hardware-based secure environment to shield portions of code and data from access or modification, even from privileged software. Privileged software in this means certain aspects of the system firmware, the OS, the normal operating system, and the hypervisor. But what does this really mean? So it establishes a separation between the system software, which is the hypervisor, the virtual machine manager, or the host OS that is controlled by the system owner, and a trusted execution environment. The system owner in this case, I will often use the term cloud service provider. Here, it doesn't have to be a cloud service provider. It could also be an edge computing provider, or honestly, it can also be the owner of a cell phone in that matter. And the trusted execution environment cannot be inspected or modified by the system software. Inspected is that inspection is typically provided by encryption. Modification is also provided by authenticated encryption modes. So, and since the system software can inspect it, the system owner also cannot inspect it. The software in the TEE, this is key, and this is actually the part that gets left out the most often, is the software inside the trusted execution environment can request generation of an attestation token from the platform, and then it can present this token to a relying party. The relying party can then validate the attestation token to know a couple of things: that the software that it is communicating with is truly running inside a trusted execution environment, and that the software that it is communicating with has the measurements that it's expecting that are reported in the token. So when you perform attestation validation, you, one, confirm that it is an actual valid token produced by a valid hardware platform, and then two, that the measurements that are in that token match the measurements that you expect. So you know that you're talking to your software running in that trusted execution environment. Only after the relying party has done this should the relying party provision secrets into their TEE, their trusted execution environment. And they can do that with confidence at this point, depending on how much trust they have in the hardware platform being presented to them. So in addition to this separation, TEEs typically also provide DRAM protection from attackers. So this protects people from cold boot attacks or just anybody who might be able to probe the pins on the DRAM bus. So and this is just generally done with encryption. Now, in addition to encryption, you also need to, and that encryption provides confidentiality. It protects your data from inspection. Providing protection from modification has resulted in some very interesting solutions because of the particular challenges of that. So typically when you encrypt data, it doesn't blow up the size of the data by any significant amount. However, when you add authenticated encryption modes, you effectively add a MAC onto the end of it, and that, depending on the size of your block and the amount of data you've got, does increase the size of your memory footprint. But for example, Intel's SGX has found some very interesting ways to provide this modification protection using Merkle trees, which, if you're not familiar with Merkle trees, basically say it's the technology that underlies parts of Bitcoin. But don't let that sour your opinion of it. I'm not too big on cryptocurrencies, but Merkle trees are really fascinating. I won't get into the details on this though. So one of the first truly confidential compute platforms was Intel's SGX. And this was done, it allowed a user space process to create a trusted execution environment that was part of its own process and protected from modification or inspection by the rest of the process and the OS and most of the system firmware. Interestingly, Intel in SGX has used their direct anonymous attestation. It's a bit more complicated than most of the other attestation protocols, but it does allow revocation of devices based only on a signature. And this is why the term anonymous comes from. And typically, if you want to revoke a device, you basically have to revoke it based off of a key, which can identify the device. But Intel's DAA allows them to revoke based only on a received signature. And then one challenge of Intel SGX is that software you developed for it needs to use a proprietary API for many of the services. Cryptography, a lot of the things you might rely on an operating system for. So porting existing applications can be difficult. That being said, in order to port that platform, it required you to rethink your securities posture, so it actually could result in more secure results. And more recently, Intel has been developing something called Grameen, which I actually hadn't been up to date on. So, but they basically looking at a low TCP OS environment that looks a lot like other environments. So if you're interested in this area, I would look up Intel's Grameen work. However, SGX is now appears to be, it's hard to say, but the industry tends to be moving towards the concept of a blind hypervisor instead of an in-process trusted execution environment. It creates a full VM that is inside the trusted execution environment. Technologies for this that are in the marketplace now are AMD SEV SNP, which was the first player in this space. Intel has released their TDX. I don't, if anyone here can remember what TDX stands for, I can't recall. If we've got an Intel person on the call, maybe they know. And then ARM has released, we've released our CCA, our confidential computer architecture. There's no CCA products on the market today, but do expect them soon. I can't speak on when that will happen. So what the blind hypervisor works at is it runs a full virtual machine inside the trusted execution environment, sometimes called a confidential VM by AMD. In ARM, we call it a realm. And interestingly, the VM OS, the confidential VM OS that's running inside the TE can be anything, but it's usually Linux or Windows, and it also includes a system firmware. So you wouldn't without I was also required to put an ARM confidential compute architecture diagram in here to give you a concept of how the system works. If you're familiar with the ARM architecture, we typically historically have the concept of a non-secure world and a secure world, and the secure world is the trust zone space, if you're familiar with that. With the ARM CCA, we're adding a realm state to the architecture, which is the one on the left there, and it can run multiple realms. You can run. It's just like any other VM. You can run any number of realms on it. And the Realm Manager is a new trusted piece of software that manages the page tables of the realms based on direction from the hypervisor. Realm memory is encrypted, and the memory of a given realm is not mapped to other realms or to the non-secure stack. So this means that the Realm Manager, are sometimes called the RMM, by us, is part of the Realm's trusted computing base. We've got the specification for the RMM has been formally proven using the Hall interactive theorem proving. I don't know a lot about this. If you have questions about that, you can contact me and I can point you to the people who did the work. They're close colleagues of mine. Additionally, ARM is working on an implementation of the RMM, the Realm Manager, that is also proven using CBMC and other tools. I also worked with the people who did that work. So if you have questions about that work, please hit me up and I will put you into contact with them. So when it comes to taking a workload, an existing, any workload, and you want to move it into a confidential VM, into a TEE. Previously with SGX, you had to do a significant amount of porting work to use the new APIs because you no longer had your operating system stack that was trusted inside your machine. With the blind hypervisor models, we can move to a lift and shift model where you take a normal VM workload, which is the one in the middle with the application, Linux, and UEFI, and you just lift it, and then you shift it and move it into a TEE. And for the most part, this can work quite seamlessly from your workload. However, what does the owner of the VM get by moving his confidential workload into the trusted execution environment? If they haven't performed attestation, which is an additional step and additional software requirements, they cannot know that it's running as a confidential VM or in a realm without attestation. And any software vulnerabilities that they had before, they still have inside their software stack. What it does do is it can give a cloud provider or an edge services provider plausible deniability. if they can prove that the VM was truly executed inside a trusted execution environment, they can say, we never saw your data. We never had any access to your data, if they can prove this. So, however, for the user, owner of the VM to get it, the VM owner of the VM has to rethink their software architecture in some fundamental ways. Now, SGX required you to effectively think about the project in two separate parts: in your secure space, which was inside the enclave, and your non-secure space, which was outside the enclave. You had to establish communication between them and establish how you could trust that communication. It required more deliberate thought about what you were doing. So if you're going to do a true confidential compute workload, you need to do that. And you still get to do that. And I will say that with these blind hypervisors, while if you're lazy, you can just move them in. But by re-architecting them, and you can still use a full Linux stack. You can use a Linux file system. You can use all of the services that Linux or Windows offer. So having taken an application and started it on SGX, ported it to AWS Nitro enclaves, ported it to AMD SEV, ported it to ARM CCA, the blind hypervisor environments are much easier to work in. But you do have to be deliberate about how you're doing it. But I do feel that the blind hypervisors make things quite a bit easier. But as I said, Intel SGX by default is more secure. So I've talked a lot about attestation. I'm going to go through a quick flow chart of what attestation looks like here. I cannot stress enough how important attestation is to a true confidential compute application. If you're familiar with attestation with TPMs, this is going to look very familiar, and this is just a broad strokes approach. First, you have the client, which is also referred to as a relying party in the RATS architecture. I'll get into that in a little bit. Issues a challenge, which is just typically a random number, to the trusted execution environment. That trusted execution environment then sends a request to the platform firmware, which is part of its trusted computing base, that part of the platform firmware that is, and that then reports back a signed token, which gets sent back to the client. Now, this next part is not entirely necessary all the time, depending on how you do it. The client then sends the signed token to an attestation service, which then comes back with a pass-fail. If it passes, then the client can extract the measurements or other data from the token and then compare it against expected values. In addition to part of this, there also can be, as part of this, there can be a Diffie-Hellman key exchange to establish a shared secret between the client or the trusted execution environment, or the signed token may contain a hash of a public key, in which case then the client can then be assured of the public key of the trusted execution environment. The attestation service takes on a lot of different forms depending on the platform in use. For SGX version 1, it required every time you wanted to validate a token, you would have to go to the Intel's attestation service to get the pass-fail result. For AMD SEV, what you do is when you get the signed token, you're actually not sending the token to the attestation service, you're sending effectively a device ID, and then it sends you back a key. And then for future verifications on that exact same platform, you no longer have to go to AMD's attestation service. For ARM CCA, it's going to be basically effectively dependent on the manufacturer of the part. So attestation is a complicated topic. And now this is where I do a shameless plug for an ARM and Confidential Compute Consortium project called Verizon, who I also work closely with this team. They provide a generic software stack for attestation services. This allows you to write your own attestation service, which then interfaces with the native platform attestation services. And you can also provision trusted measurements and things of that nature, so you can offload establishment of your norms or what your hashes are. What I've also mentioned before is the remote attestation procedures, RATS architecture, which is also being developed by the CCC. This provides a common language for the various attestation architectures and the players inside the attestation. Another shameless plug from some colleagues is the attested TLS solution, which is basically integrates attestation into the TLS handshakes. This was Thomas Fasati is one of my coworkers, and also a former coworker of mine, Hannes Schoen. I honestly don't know how to say his name. He was always Hannes. Hannes Schoenflight. His name starts with a TS. I'm sure you know who he is. He was a former colleague, but he's still working on this. One thing to note about attestation, if you're doing attestation naively, as the number of nodes in the network increases, the number of attestation scales as O to the n squared, which is not a great scaling factor. It creates a lot of load for attestation services. And one of the questions I have for the SRC is, can you improve this? And now this is the areas for further research. One thing that everybody knows about, if you've followed this at all, is that there are side channels on CPUs. These side channels are going to always be there in one form or another when there are shared resources. So the biggest concern I have for confidential compute is, how do we quantify the bandwidth of a given side channel? How much bandwidth do we have is acceptable for a given application? How can we affect the bandwidth of a side channel by the way we write the software? And what I think is a really interesting area, especially for the people at SRC, would be, how do we holistically quantify the bandwidth of a side channel, especially before tape out? So can we create, if we look back at cryptography from 20 years ago, it wasn't a very formal methodology. There wasn't the concept of advantage. There wasn't the concept of authenticated encryption. And I think we needed to go through that type of rigorous theoretical work on side channels so that we can have a holistic system for understanding what a given architecture or microarchitecture really will have, what kind of side channels, and can we do this before tape out? So when we produce a part, we will know what those side channels are. Another area for further research is databases and file systems. Both of those bleed metadata. If you've got a trusted execution environment talking to a disk that's outside that trusted execution environment owned by the platform owner, you will always bleed information. The timing of your accesses, not always actually, there are exceptions, but the timing of your accesses, the size of your accesses, you don't want to, from a cryptographic perspective, you don't want them to be able to tell you're accessing the same piece of data twice. You don't want them to be able to tell the difference between a read and a write. And in order to do that right now, the state of the art appears to be something, if you know something more than me, this is great. But the state of the art appears to be obfuscated random access memory, called not memory, obfuscated random access machine, sorry, which is remarkably inefficient. So it basically breaks out your structures. The state of the art right now breaks it into a binary tree structure. Every time you read, you traverse all the way down the tree. Every time you write, and you also have to rewrite the tree. And every time you write, you traverse all the way down the tree, and you have to rewrite the tree, because you have to do that rewrite. Otherwise, they would be able to tell the difference between a read and a write. ORAM is very inefficient. However, there are entities that do use it. I actually was mistaken a few months ago when I said that no one's ever going to use ORAM. I told my managers this, and then it turns out the Signal, the private messaging application, which was one of the most prominent users of SGX, is also using ORAM for their contact discovery algorithm. And they actually got a lot of improvements from it because of they were paranoid from the beginning. They're continuing to be paranoid, but ORAM gives them those solutions. But can we improve this? Right now, for most use cases, ORAM is not a viable solution. So that's the question. That's another question that comes up. One area that my group's been very interested in is we'd like a low TCB, a low trusted computing based operating system that can run inside the TEE. Currently, most blind hypervisors are running Linux or Windows inside the TEE, and Linux and Windows are large. Is there a low TCB OS that has a rich programming environment? We haven't found one. We've been trying on various things. The rich programming environment tends to be the big problem. So it's possible that these two goals are incompatible. One thing that I did learn while presenting the slide, Intel has also been working on this, and I need to look closer at that work. Attestation is another issue that comes up. Most users in a lift and shift model are not going to perform attestation. They just aren't. So how can a CSP, a cloud service provider, or an edge service provider prove after the fact that their customer was in fact operating in a trusted execution environment? There's a bit of work going on in this area, but I think there's a lot to be learned in this area as well. And then what if a cloud service provider is the silicon designer? What we have right now, if you're running, for example, AMD SEV inside Azure, you've got separations of concerns between them because you're perceiving that you're trusting the AMD platform, but you may not trust your cloud service provider. What happens when the cloud service provider is the silicon designer? Can we establish trust in hardware when someone doesn't trust the holder of that hardware, or actually the creator of that hardware? I think this is a capital H hard problem, but it would be really interesting to see work in this area. And now I am ready for questions.
Thank you, Derek. I find this very interesting. So questions to Derek. Okay, Kanat?
Yes, Derek, I have a question. Excellent short presentation of everything. The question I have is, how does the ARM solution handle shared confidential data across VM?
As it currently stands, we don't support it. So if you want to do it, you will then have to work out through the host. What you would have to do is have two realms, which would then establish a shared secret between each other using an attestation procedure. And then from that shared secret, they then are able to move the data, and they have to basically use a shared memory buffer offsite on the host side. And so they have to do their own encryption on that.
So there is no direct solution. That's a short answer, right?
At the moment, yes.
Okay. The second question I have is, there is a lot of announcement that I saw about capability-based hardware that came out of Cambridge from Robert Watson's group, and there are plans to productize it. That would offer you many of the advantages you have of need for confidential computing, data sharing, etc., in a secure way. What's happening to that? Is there something you can talk about?
So, are you referring to the Cherry work out of Cambridge?
Yeah, it's the Cherry work.
Oh, it's for the most part, and I'm not especially well versed on Cherry, but for the most part, Cherry for me capability is largely about protecting what software can do in and of itself. So limiting its access to memory outside of its footprint, or basically using authenticated pointers in that. That's the area of it that I'm familiar with, and I'd say it's a very interesting but largely orthogonal to confidential compute. There's another side of his work that I'm less familiar with, so I can't speak to it. As far as productizing any Cherry work, I'm afraid I can't speak to that either.
Thank you.
Yeah.
Thank you, Kanat. Derek, John?
Yeah, it's Schwenig, Derek.
So thank you so much. I never get it right.
It used to work for me, so I practiced it over the years.
Hannes, by the way, I want to let everybody know he's talking about Hannes Schwenig, who is one of the authors of the attested TLS.
TLS Hannes actually wrote most of that when he was at Nokia before he came to ARM. Just in answer to your question, the place to go looking for all the Cherry stuff is that there's a program in the UK that ARM still participates in called Digital Security by Design. And if you want, I can put you in touch.
No. So John, I'm very familiar with that. I had a parallel DARPA effort with, Watson for a while. So I know the effort, but I was curious how much of that was really, transitioned into products.
Yeah, but
Cherry has, for the record, Cherry has a lot of inefficiencies.
Yeah. If you're interested, talk to a chap called John Goodacre. He's a prof at University of Manchester who runs that program. And then I have a question for Derek. Can you be a bit more specific about when you say low TCB? Do you have a target in mind there in terms of footprint?
Not any specific numbers on it. It was the work that we were doing was largely looking at things like SEL4,
Yeah.
which is what I think was it 400K? Is that
Yeah,
the
yeah.
for that? That was the type that we were looking for. We weren't looking for like sub 100K, but we were looking for, you know, something let's say less than a megabyte of footprint, just because of the just the more code you have in your TCB, the less happy you are, the less confident you are in it.
Yeah.
So it was on the order of, you know, 500, maybe a megabyte.
And it's the assumption that you would want to bake that into ROM essentially. And that's why.
You don't have to bake it into ROM, actually. That, as I said, this OS is just part of a VM image, so you can pull it in at any time. I mean,
Okay.
It doesn't have to be part of ROM, but the concern actually just is the more code that you have in your trusted computing base, the more likely there are to be bugs, and that's the concern with the low TCB OS. You can minimize Linux in a lot of ways, but you're still working with a very large code base written in C, which which is going to have there are problems in it. There just always are going to be. And the less code you have, the fewer problems you will have. So,
Yeah. Thanks.
Thank you, John. Thank you, Derek. Thank you, Kenneth. Other questions to Derek before we move on?